Okay, so last time, just to remind you, last time what we did, we obtained, so we are looking at this differential equation, z times 1 minus z d2u by dz2 plus, I think, c minus z du by dz, and minus ab u equal to 0. And the general solution of this was, I mean, we represented the solutions by the symbol, Riemann P symbol, which had all the basic information was there. So these were point 0. One of the singularities is point 0, the infinity and 1. And here the solutions, the initial equation, 0, a, 0, 1 minus c, b, and c minus a minus b. So this was the general symbol. Then we said, looking at this here, we see that there is one solution. If you make a power series expansion, I mean, there is one solution which is analytic at z equal to 0. Similarly, there is one solution which is analytic at z equal to 1, right? And the solution which is analytic, so the solution which is analytic at z equal to 0, let's call it u1. So we call it u1. And that u1 is defined as simply f, a, b, c, z. So this is a definition of f. This is symbol f. And this is called the hypergeometric function. Okay. And we normalize this, I mean, obviously, given a solution u1, I can always multiply by some number. It will again be a solution. So we normalized it in such a way that when I make a series expansion, it starts with 1. 1 plus some coefficient times z plus so on and so forth. So we normalize it so that the constant term is 1. So in other words, what it means is that f, a, b, c, 0 is 1. Okay. That's normalization. And then we found that this FABC, we obtained the power, we made the series expansion and plug it in here, and we obtained a recursion relation for the coefficient Cn. And from that, we deduced that the expansion was simply this one, gamma C, gamma A, b plus n divided by gamma 1 plus n times z to the n, where this constant is precisely designed to make this coefficient this equal to 1. Because you see, for n equal to 0, the z to the 0 term just comes with a gamma A, gamma B divided by gamma C. So all that cancels, and gamma 1 is 1. So this is just done to make sure that the coefficient of FABC 0 is 1. That's the only reason. Okay. Furthermore, we also looked at all the other solutions. For example, we obtained the U2. So this was the U1. And similarly, we obtained U2, which was, we should go like z to the 1 minus c, the starting power. So this was given in terms of z to the 1 minus c. Okay, I will not write down all the things, but we had, I think, obtained all of these expressions. Yeah, it was some. It was again another hypergeometric function, which was sorry, what was it? F b minus c plus 1, right? That's yeah. B minus c plus 1, a minus c plus 1, and then 2 minus c z. Okay. So these were the two linearly independent solutions. And this had a power expansion near z equal to 0, because this hypergeometric function f has a power series expansion near z equal to 0. So this also has a power series expansion near z equal to 0, with different coefficients, of course, because now a, b, c have been changed to these values. No? So there will be different power series expansion. And these were the two linearly independent solutions near z equal to 0. Well, that's it. I mean, these are the two linearly independent solutions in general. However, as I said, these are not very convenient. These power series expansions are not very convenient if you want to study how this function behaves near z equal to 1, right? Because I mean, the radius of convergence of this series is z equal is 1, right? So if you want to understand near z equal to 1, you really have to sum up the entire series, right? Which is very difficult, right, in general. So, so then it is more convenient to use a power series expansion already in 1 minus z if you want to study near z equal to 1. And then we again wrote down two independent solutions as power series expansions in 1 minus z, and those were, yeah, I don't know. I mean, those are, I will not write down. They were given in 17, let me see, what was it? 17.14, yeah. So one of them is 17.14, other was 17.15, right? And then, so this was near 1 minus z, so near z equal to 1. And then there were two solutions which we, if you want to study what happens near z equal to infinity, so then again, none of these solutions are very useful. So then the more useful thing is what we call U1 double tilde, U2 double tilde, and those are given in 17.16 and 17.17. So this is near z equal to infinity. Okay. So these were the solutions. Right? Of course, as you said, there are only two linearly independent solutions, which means, for example, this I should be able to express as a linear combination of these two, right? Similarly, so all of these four of them, I should be able to express as linear combination of these two. I mean, I can choose any two fundamental, or vice versa, I can choose these two as the linearly independent objects. Then everything else I should be able to express as linear combination of them. Right? So this is the main thing. Yeah. Sorry. Yeah. Everywhere. Yeah, I mean, this is everywhere. I mean, in the sense that, so this is a power series expansion near z equal to 0, right? This is near z equal to 1 and so on. So if you draw this here, so this is z equal to 0, z equal to 1, 1. So for example, these two I can trust in a region which is inside this unit disk. This series makes sense only there because that's the radius of convergence. Whereas if you look at these two expressions, which are power series in z minus 1 or 1 minus z, then that would be in this region, right? And if you look at these expressions there, the hypergeometric function which appeared in these expressions, the argument was 1 over z, right? So 1 over z should be less than 1, right? Which means z should be greater than 1. Modulus of, so z must be greater than 1. So which means these two are defined everywhere outside this unit disk. So basically everywhere you have some, I mean, all of these have some overlap region. For example, if you look at these guys and these guys, there is this overlap region, right? If you look at, if you look at this and that, there is an overlap region which is here, right? These two do not have directly an overlap region, but you can go from here, from these guys to these solutions by matching in the overlap region, and then analytically continue there, right? And then similarly from here, and these you can again, there's an overlap region here, so you can analytically continue from there to there, right? I mean, so in principle everywhere is defined. I mean, it's defined everywhere, except that in practice is, I mean, if I want to study how this function behaves somewhere here, right? It's, I mean, it's not very convenient to use these series expansions. You must do a series expansion here, right? There, of course, when you do the series expansion, I mean, this is an ordinary point, right? So both the solutions will be analytic there, right? And so, I mean, all the expressions are there, but it may not be very useful to study the behavior at some point. But in reality, in most of the problems that one encounters, really the interesting phenomenon happens near the singular points. So one needs to understand the behavior near the singular points, and for that, these functions are more useful. Okay, so now there are two things I would like to do today. One is the, what do you call it? To show to you that indeed, I mean, if I, for example, take this solution. Well, I mean, if I now go start, I mean, as I said, this is defined in the unit disk, this one. Now, as I start moving z close to 1, somehow I should be able to, I mean, after all, we know that this is going to be a linear combination of these two. Oh, I just erased that. Now, let me just keep the symbol P, 0, infinity, 1, because this has all the information. 1 minus C, A, B, and this was 0, C minus A minus B, Z. So if you look at this U1 tilde and U2 tilde, which are near Z equal to 1, one of them will be analytic, right? And other will have this, so one of them will go, this one, say, for example, goes like 1 minus Z to the 0 times the series expansion in 1 minus Z, whereas this one will go like 1 minus Z to the C minus A minus B times the series expansion, right? In integer powers of 1 minus Z, right? So we are saying that this U1, after all, is a linear combination of these two. So near Z equal to 1, it will have, near Z equal to 1, okay, this is analytic, but this will, there's a branch cut here in general, right? If C minus A minus B is not an integer, there will be branch cuts. So one should be able to see that. I mean, so the question is, how do I see this from this series expansion, right? So first, that's the first thing I will try to just convince you, and that's also a good application of Stirling formula. So, I mean, this is something that we have seen. Remember, the gamma functions, argument of the gamma function, if it goes to infinity, Stirling formula gives you a leading behavior, right? How it diverges in the large. So, for example, see here you have all this. Okay, so what is our idea? Here this infinite series. If I just look at some finite number of terms, right, those finite number of terms are never going to give you any singularity near Z equal to 1, because it's a polynomial, right? At Z equal to 1, it will be perfectly regular. Okay, so if at all you expect to get something like this behavior, that should necessarily involve really summing over all the terms, right? So therefore, it becomes crucial that really what controls these singularities here is really the large n behavior of these coefficients. So to give you an idea, let's see. So suppose I have some, let's try to look at this 1 minus Z to the C minus A minus B. And let's try to make a power series expansion of this quantity near Z equal to 0. Okay? So let's try to see how it looks like. So if I expand, in fact, let me just write it like this, minus alpha. Alpha could be any number, and later on I will put alpha equal to A plus B minus C. So if I want to make an expansion, well, it will go like 1 plus alpha Z. So make a Taylor expansion near Z equal to 0, right? So the nth term, okay, so 1 plus alpha Z plus so on and so forth. Nth term would be simply take 1 over factorial n dn by dzn of this quantity, 1 minus Z to the minus alpha, evaluated at Z equal to 0 times Z to the n, right? That's a Taylor expansion. This is Taylor expansion because at Z equal to 0, there is no singularity here. It's analytic in Z equal to 0, near Z equal to 0, right? So I can do this. So let's take n derivatives. What am I going to get? I will get minus alpha minus 1, minus alpha minus 2, all the way up to minus alpha minus n minus 1, right? Times 1 minus Z to the minus alpha minus n and divided by 1 over factorial n. That's what I will get. But then I have to substitute Z equal to 0, so this just becomes 1, right? So this becomes 1. So that is this coefficient times minus Z to the n. Well, actually, if I make actually each of them is plus, in fact. Huh? Each of them. When I take a derivative, I'll get a minus alpha, but then I have to take the derivative of here, so it becomes plus here. So each of them is plus finally. So that's what you get, times Z to the n. That is the expansion. But this expression, I can write it as gamma of alpha plus n divided by gamma of n plus 1, or 1 plus n, let's say, right, from here. And then I have to divide by gamma of alpha. Yes? Because gamma of alpha plus n divided by gamma alpha, by using the recursion relation, this relations for gamma of alpha plus n equal to alpha plus n minus 1 times gamma alpha plus n minus 1, and so on, right? You keep doing it again and again, and then finally this ratio will be exactly that, the numerator. And factorial n is simply gamma n plus 1. Right? So this is these are the coefficients if you expand 1 minus z to the minus alpha. Okay. So that's, whereas here we have this expansion, right? So question is, I mean, if we expect this to behave like this U2 tilde solution, again, as I said, U1 tilde is, you will not be able to see from this kind of thing, because anyway, even if I look at the finite number of terms, that will be analytic in near z equal to 1. So this can always be there. So we are not going to probe, by this method, we are not going to probe whether U1 tilde is there inside or not. For that, we'll need to use different methods. But if this has, I mean, this will be, we say, a linear combination of these two, right? So, but if this, if U2 tilde part is non-zero in this in the linear combination, then I should see this behavior, right? So, so then the question is the following: whether if I look at large n behavior of this coefficient, whether that is the same as a large n behavior of this coefficient for alpha equal to a plus b minus c. So we should see, I mean, if the statements are all true, we should see the large n behavior of this is the same as a large n behavior of these coefficients for when alpha is equal to a plus b minus c, right? That's what we should see. So for this, we need to use Stirling formula, both sides. Here also, because both we are studying large n behavior, right? So large n behavior, we need to see, to use the Stirling formula for these gamma functions as well as Stirling formula for these gamma functions, and then see whether the two things are the same. Okay. So let's remember what is the Stirling formula. I brought that expression. Yeah, Stirling formula was this. So gamma of z plus 1 behave like, okay, some constant factors, root 2 pi. These things will not be important. Maybe I shouldn't use this z, not to confuse with this. Okay, let me use x plus 1. I mean, not to confuse with this z. Gamma of x plus 1 was root 2 pi e to the minus x and x to the power of x plus half. Okay. So let's see, I mean, so suppose I want to compute something like gamma of n plus a in the large n behavior. So this is x goes to infinity, right? So here I want to look at n going to infinity limit. So, well, that's the same as, you can write it, I mean, after all, just you can add and subtract, right? Minus 1 and plus 1, okay? So this you can take it to be x, this is and substitute that there. So this behaves like root 2 pi e to the minus n plus a plus 1. So just take x minus 1. So just take x equal to that. Because a is something fixed, right? I mean, when you say x goes to infinity, the same as n goes to infinity is here. These are this finite quantity. And then you have n plus a minus 1 to the power of, or even better, I can write, okay, let me do in two steps, a minus 1 to the power of n plus a minus 1 plus half, so minus half. Right? This is the general behavior. Okay. So let's try to work out this, all these terms we need to work out now. So we have, okay, let's start from here. So what do we get? So root 2 pi I don't need to worry about, because you see there are 4 factors, 4 gammas. Each of them, the argument is going to infinity. So I'm going to use the Stirling formula of each of them. So these root 2 pi's will cancel, numerator and denominator. So I don't need, I think I need to just mainly look at the n, this remaining part. So you get, from the top, you get e to the minus n plus a minus 1. And then times n. Okay, at this stage, let me take out n from here. So you get here 1 plus a minus 1 divided by n. Okay, so you get here n to the power of n plus a minus half, and then 1 plus a minus 1 over n to the power of n plus a minus half. Okay. That's one. Times the same thing with a replaced by b. Right? I mean, this is the same. It's just a replaced by b. And then divided by the same thing with a replaced by 1. And then multiply same thing with a replaced by c. Right? So this is the ratio. Right. Okay, then there's an overall factor in front, but let me just focus on this inside. Okay, so remember, this is I should write it down somewhere. So I can erase all this. The behavior of 1 minus z to the minus alpha is expansion gamma of a plus n, alpha plus n, divided by gamma of 1 plus n, and 1 over gamma alpha. Okay, this is, you see, this is n independent, so I could have taken it out. This is n. Right, so that's. So now let's try to work it out, what we get here. So when I take this, all of this contribution, you see, first of all, e to the minus n will cancel, right? Because there are each of these terms. I mean, this term, this term, this term, each of them comes with e to the minus n. So that will cancel. However, this will not cancel. This will stay, a and that is b and so on. So this exponential factor is simply e to the minus a minus 1 plus b minus 1, and then minus, well, a minus 1, when a is equal to 1, this factor vanishes. Right? And then you have a goes to c. So, but this is the denominator, so it will become minus c plus 1. That's, and then you have n to the power of n. So you have n to the power of, again, n to the n will cancel from 4 terms. So you get here n to the power of a minus half plus b minus half minus 1 minus half, which is minus half, and then minus c plus half. Okay. This is a plus b. So what is this? So that's the n power. And then there will be these factors. But these factors, okay, I don't think they're so important. We don't need to worry so much about it. It's mainly the n power which is important. The reason is, I don't know if you know this, 1 plus 1 over n to the power of n in the limit n goes to infinity is simply exponential e. Okay, but so some constant. I don't need to worry about that. I'm looking at what is the n behavior here. Okay, that's more important point. Constants are not important at this stage. I mean, constants will be important if you really want to extract, if you want to really say that this is equal to some number times that. Okay, but at the moment I'm not interested in that number. I'm only interested in whether this behavior exists or not. So I will not worry about these factors. This will be, yeah, because anyway, so I mean, in general, if you have some beta to the power beta divided by n, this e to the beta. Yeah. How will one see that? I think you can just take log on both sides, log of both sides. Take the log of this side. Log of this side will be n log 1 plus beta over n, right? But we are looking at large n limit, so this is a small quantity. I can make an expansion for the log. So that is simply n. The first term is beta divided by n. Then the higher powers, which will be of order 1 over n square, right? So this is not important because that will be 1 over n down. So the important point is this one, which is just beta, which is indeed the log of that. So you see that this in the large n limit, this goes like that. Plus order corrections, order 1 over n corrections and so on. But we're not interested in that. Okay. So as I said, so ignoring all the constants, this is what we get. The n behavior is that. Actually, you can even keep, leading behavior is that, so you can even keep that. So what we have from here, you get e to the a minus half. From here, a minus 1. These are not important. You see, the only important point is the n. Because other thing is just, in the n goes to infinity limit, if you just look at this power, forget the n, this n, as n goes to infinity, this is just 1. So 1 to any power is 1 again. Okay? So this is not going to enter. So you just get e to the a minus 1. There you get plus b minus 1. And then a equal to 1, that drops out. And then you get here minus c plus 1. So in fact, even you see that this a, b, c also cancels, right? Actually, in fact, this entire thing cancels. So it's 1. Yeah. So, okay, so that's what we have. N to the power of, so let's collect all that. So a plus b minus c, and then minus 1, right? That's what you get. That is the inside thing here. Okay. Now let's look at this coefficient, the large n limit. Again, you have to use Stirling formula. Okay. So you get here gamma alpha plus n divided by gamma 1 plus n. Well, it's the same as taking alpha a equal to alpha here, right? In that expression. I mean, this was just expansion of, this is what we said is gamma a plus n, right? In the Stirling formula. So now just replace in this expression a equal to n alpha. So you find this goes like e to the minus n plus alpha minus 1, n to the power of n plus alpha minus half, and then 1 plus alpha minus 1 over n plus alpha minus half, divided by the same expression, just replace alpha by 1, right? So this is e to the minus n to the power of n plus 1 minus half, and then 1, 1. I mean, this is just 1, right? Because 1 alpha equal to 1, that drops out in this case. So once again, n cancels with that. And so this is the behavior, and this just gives you e to the power of alpha minus 1, which cancels with that again. So this whole thing cancels with that, and you just get this behavior. Sorry, there is also 1 minus 1. So n cancels. So again, n cancels. 1 minus half is half. So it goes up. So n to the alpha minus 1. So this behaves like n to the power of alpha minus 1. And that, so this is the expansion of this guy. And expansion of this guy behaves in the large n limit, behaves like that. Compare the two things, and you see alpha is equal to a plus b minus c, which is what you wanted. Huh? Alpha should be equal to a plus b minus c. Right? So you see that in the large n limit, I mean, near z equal to 1, so near z equal to 1, we need to sum up all the terms, infinite number of terms, and we see that the leading behavior is the same as 1 minus z to the power of a plus b minus c. The leading behavior is simply 1 minus z to a plus b minus c, right? Which is what you expect for the U2 tilde solution. I mean, this is just, I mean, I wanted to do this exercise just to show you that you have this analytic function near z equal to 1, this is an infinite series, but when you sum up the series, somehow at some other point, you get singularity or branch points and so on, branch cards, etc. when you sum up the series. So this is just a concrete example of that. So, and also to show you that indeed, when you expand U1, it will in general be a linear combination of these two. This one is analytic, so you don't see by this method, but this one you see by this method. Yeah. This is from the Stirling formula. Stirling formula. You remember in the second chapter, this is the Stirling formula, where what we did, you remember we had the expression for gamma, which was, it was the integral expression for gamma, right? I think it was gamma z was e to the minus t to the z minus 1, something like that, dt. I think it was like that. And then what we did, we tried to evaluate this integral for large real part of z. The real part of z is large, positive infinity, right? Large, very large. In that case, we use the steepest descent method, saddle point approximation, to evaluate the integral. And we found that in that approximation, it gives you this behavior. So in other words, gamma of z plus 1, let's say gamma of z plus 1. So then this becomes that, right? So then we showed that this behaves in this way. But that was from the using saddle point approximation. So it was a kind of example of how to use saddle point approximation when we did the saddle point method. So, and here is again an application of the Stirling formula. Okay, this is one thing. Now, but let's, I mean, yeah, so what should I do? Okay, so next step, if there's no other question, what I will do is I will try to obtain another representations for these solutions, all these U1, U1 tilde, all of these solutions, different solutions, as an integral, in terms of an integral, a contour integral. This is what is called integral. Such a thing is called integral representation of the solution, because you're representing the solution by means of an integral. And that's also very convenient for many things, because once you have the integral, even though you see this particular thing, in order to study near z equal to 1, you need to sum up the infinite number of terms. But once you have integral, it's much more easy to study what happens near different points, z equal to 1 or no. And furthermore, also with this integrals, you will be able to much more easily obtain, say for example, U1, what linear combination of these two it is precisely. Yeah? I mean, this method doesn't tell you which linear combination. It just tells you that in this expansion, certainly U2 tilde exists, but we don't know about U1 tilde, right? So with the integral representation, we'll be able to do all that. So I will describe the integral representation. In fact, also it is useful because in many of the physics problems, many times hypergeometric functions come first by means of, not from the differential equation, but actually when you try to compute something, you directly find an integral. Okay, and then that integral you can identify. Okay, this is hypergeometric function. So instead of finding the differential equation to which we are finding the solution, you directly get an integral in many applications. So it's also useful from that point of view. In fact, I mentioned to you that hypergeometric functions appear in two-dimensional conformal field theories, and many times those as correlation functions. Many times those correlation functions directly appear as integrals. So you can. Okay, so this is the basic idea here, is to try to write this solution to this original differential equation. So the original differential equation was z2 plus c minus a plus du by dz minus ab u equal to 0. And okay, just try to write u as okay, I mean, this is, so let me write it like this, integral representation. So I will try to write an ansatz. So the idea is to write an ansatz, first of all. Right? You know what is an ansatz? Ansatz is just a way of, I mean, you choose some test, you test function, plug it in and see whether it makes sense or not. It may or may not work. It's a kind of a trial. So z minus t, what is that? Z minus t to the lambda times some function f of t. Let's call it f of t. F of t dt over some contour. Okay, we have not specified what contour, but just let's start with this kind of an ansatz. So t is some complex variable, and I'm integrating the t over some so there's a t complex plane of t, and this c is some contour inside this complex plane, and I'm integrating the expression and try to see if by choosing some suitable f, whether it can solve this differential equation, whether this u is a function of z. This z is appearing here. So as far as this integral is concerned, z is some fixed complex number, right? But for every choice of this fixed complex number, this result of the integral will be in general different. So it will be a function of z. The result of the integral will be a function of z. Okay. So we plug this in here. So what will we get? I mean, the only z appears is there, right? There's no z here, so every differentiation only like there. So you will get, so when two derivatives act here, I'll get lambda times lambda minus 1, right? Times z minus t to the lambda minus 2. And then I have here z times 1 minus z. Okay, so that's the first term. Then you get here plus c minus a plus b plus c minus a plus b. Sorry, what is this? A plus b minus 1 plus 1? Ah, plus 1, correct. A plus b plus 1 z. And now I just have one derivative, so you get here lambda times z minus t to the lambda minus 1. And then finally the last one is simply minus ab to the lambda. And this whole thing is multiplying f of t dt, and I have this contour integral. Right? That's the left hand side when I just plug that in here. And we want to make this 0. By appropriately choosing lambda, we have freedom to choose a lambda and this function f of t, right? And in such a way that we want to make this 0. So first of all, okay, let's see this. I can take out some common factor. Z to the lambda minus 2 I can take out, right? Z minus t to the lambda minus 2. I take out as a common factor. So this goes out. So this goes out. Here I have lambda minus 1. So if I take out lambda minus 2, then there will be 1 power left over. And here 2 powers will be left over. Once I take out as a common factor. Because this was lambda originally, I'm taking out lambda minus 2, so I'll have 2. Now this whole thing is, as you can see inside this square bracket, what we have is a quadratic function of z, right? You see this is quadratic. This is linear, but that's also another z there, so it's quadratic again, and this is also quadratic, right? So what I will do is I will choose lambda in such a way that the z square term vanishes, right? So that it will become a linear function of z. Okay. So let's collect all the quadratic terms. So the coefficient of z square inside the square bracket, you have a minus lambda times lambda minus 1 from here. And then from here you get this product. So it's minus lambda times a plus b plus 1. I mean, it's just this coefficient, z square. I'm looking at the z square term. And from here I get minus ab. Okay. And then order z. Then z times some coefficient plus some 1 times some coefficient. This is what the structure of that is, right? So what I'm going to do is I'm going to choose lambda to make this vanish, so that inside the square bracket you have only linear function of z. So, this just a quadratic equation for lambda. It will have 2 solutions, right? I want to set this equal to 0. So you can see, let's see, minus lambda. So this is the same as I can take out minus outside. Okay, so you get lambda square minus lambda, but that minus lambda will cancel with this plus lambda here, lambda times 1. So this goes out and that goes out. And then you just have a simple equation, a simple quadratic polynomial of lambda square plus lambda times a plus b plus ab, right? Which is the same as lambda plus a times lambda plus b. So there are 2 solutions. Either I can choose lambda equal to minus a or lambda equal to minus b. Both, you can choose either of them. You'll just get 2 different integral representations. But so let me just choose lambda equal to minus a. In that case, this vanishes. So, and now we just look at the linear term. So what's the linear term now? Linear term is here, lambda times lambda minus 1. So let me write down explicit linear term now, z, lambda times lambda minus 1 from the first term. From the second term, I have 2 pieces. So minus ct, minus t times that. So plus t times a plus b plus 1, right? I mean the cross terms. You look at the cross terms times lambda. And then there is z times c. So plus c lambda. Lambda is always there. And then finally, the cross term is plus 2ab t. Right? That's the z term, and then the order 1 term is, I mean, the z independent term here there is nothing. Here you have ct, so minus ct lambda, and then from here you get t square, so minus ab t square. Okay, so that's the whole thing. And now I substitute lambda equal to minus a. So that a minus a, this disappears. So this becomes a times a plus 1. Here you get minus a times this. This is minus ac. And here it's plus a. Okay. So this is what we have. Huh? Sorry? Sorry? How? Maybe I know, I think I made a mistake. It's possible. Huh? It's okay? Or? No, I mean, this was, I just substituted lambda. I don't know, maybe I may have made algebraic mistakes in doing this. Okay, so now, so what is the next step? Yeah, well, if this has to vanish, I mean, if you could write it as some total derivative term, you see. I mean, this, after all, I'm integrating over t. When, so this is still integral over t. Suppose I could write this whole thing as a total derivative in t, right? Then, in principle, it could vanish, provided you choose the contour appropriately, right? For example, if you choose an open contour, if you choose such a way that at the end points, suppose you, so there are two steps. So the idea is that suppose I can write this whole thing as a total derivative in t, right? Then the result will be simply the boundary terms, right? And if you choose the contour in such a way that the boundary terms vanish, then you're done, right? So this is a strategy. So let me see how you, so once you have removed the z square, I mean, it will become clear why we try to remove z square. As we proceed, we'll see how, why, I mean, you may ask, why am I doing this? Why, but you'll see why that's the case. Okay. Good, so. Now I will try to write this as a derivative. So let's see. So lambda is also minus, lambda is minus a here, right? So this is minus a, minus 2. Now what I claim is that this whole thing I can write it as a total as a derivative on z, as for z minus. So I want to write it as a derivative on this. So let's try to do it. A times a plus 1. I mean, let's see if this works or not. So a times a plus 1. What is this? T square minus t. I don't see. Did I make some mistake in the? There's t square. What did I do? Okay, so this is still z, right? I mean, there is this linear term in z, that is the quadratic term in, independent of. Now, what we have, this whole thing is multiplying this quantity, right? So what we have is this times z minus t to the power of minus a minus 2, and then you have f of t dt. So this is finally the integral which is left over. Okay, so what I want to first do is to write it as a, I mean, this is just a z, right? So let me write it as a polynomial in z minus t. After all, it's a linear function in z. If I write it as a polynomial in z minus t, it will be again linear in z, polynomial in z minus t, which is very simple. Here you just add and subtract, minus t plus t, right? Then z minus t term, and then there is this term you put together here. Okay, so there are two types of terms. One is coming with I mean this term z minus t times that will make the power minus a minus 1, right? But the other term, the remaining terms, will keep it minus a minus 2. So there are two types of terms. So one of them is z minus t to the power of minus a minus 2, and that is simply multiplying this term, sorry, the constant terms. So what you have, so that bracket is a bit long. It's t times all that, t times a plus 1. It's a bit of a long calculation, but I mean, okay, t square minus t square a plus b plus 1 minus act plus 2ab t square from there, and then from here, this I have to take all the things together. All that is coming with power minus a minus 2. So that's plus cta minus ab t square. Okay, that is this term. And then there is a term, so plus z minus t to the power of minus a minus 1, and that is simply taking this part of the thing and multiplying with that, right? But that's just coming with all of this coefficient, so that coefficient is simply a times a plus 1 plus t a plus b plus 1 minus at, and then minus ac plus 2ab. That is what all of this inside thing is there. This whole thing is still multiplying f of t. Okay, all that is there. So, okay, this whole thing is multiplying f of t. Okay. Now, let's see if there's some simplification occurs here. Yeah, so, for example, here, I mean, this ab term cancels, right? Minus ab, this one, and then cancels with that 2ab t square, and furthermore act also cancels with that, and this is simply a plus 1. So what you find is that here is that this whole thing is a plus 1 times t 1 minus t, right? Because there's a t and a t square, so t I can take off. This one is more complicated. Okay. So now what I can do, you see, I mean, this expression, I mean, if you look at this term here, this term is the same as two derivatives with respect to t of this thing raised to the minus a, right? So the first term, I write it as d square by dt square times a plus 1, a plus 1 times, no, not a, t times 1 minus t times d square by dt square of z minus t to the minus a, correct? Let's see. So first derivative, I get minus a, but then there's another minus coming from d by dt acting here, so plus a, and this times minus a minus 1. So second derivative will give you a plus 1. So a times a plus 1. So this first term I can write it like this. And the second term, so this f of t is still multiplying everywhere. And the second term is, let's see, so there's a factor of a everywhere, common factor, right? So combining this a, so what is left over here is a plus 1 minus t times a plus b plus 1 minus ac minus c plus 2bt. This whole thing multiplying d by dt of z minus t to the minus a, right? So you see what I have done, I have written both of these terms as some derivatives acting on this factor, z minus t to the minus a. Okay. So actually z minus t to the minus a is a common thing, so I can take this out. Okay. So this is a differential operator, it's a second order differential operator in t, sorry, this is t. Okay, acting on that. Okay, now suppose I do a partial integration, okay, and choose f in such a way that this, when the adjoint operator of this, so there's still a contour integral here. So if I choose f of t such a way that the adjoint of this adjoint operator of this okay, annihilates f of t, then we are done. Okay. So now the point you see here, why did I get rid of the z square? Is if I had not gotten rid of z square, I mean here you see there is a d2 by dt2, two derivatives and one derivative. Okay. Why it became two derivative and one derivative? Why not? I mean a general second order differential operator will have also a constant term. I mean no derivative term, right? But why there is no derivative term? That is precisely because I got rid of z square. You see what I have done? I mean, if suppose I had not gotten rid of z square, suppose it was I had chosen some other value of lambda, not lambda equal to minus a, okay, some other value of lambda, then this will be not vanishing, right? In which case, when I try to write it as a polynomial in z minus t, there will be also a z minus t whole square term, right? You see what I did? There was a linear term. I wrote it as z minus t plus t. Okay, since it was linear in z, it's going to be linear in z minus t, right? So there will be only two terms. One, which is this times z minus t, which means minus a minus 1. Okay, another with just the constant term, which will be z minus t to the minus a minus 2. Okay, so there is one step down compared to minus a and two steps down. Okay, which means there's a derivative d by dt and d2 by dt2. But if I had a term which is z square, which means z minus t square, that multiplying this will give you z minus t to the minus a, in which case I would have something which another term inside this second order operator which with no derivative. You see, that is the thing. That's the reason why we chose lambda such that this vanishes. Okay, because now you see I'll be able to very quickly find what is the solution for ft, because when I look at the adjoint operator, that's going to be I mean there's both there's a d by dt sitting here, you see, and that will allow me to very quickly calculate what is f of t, which will be annihilated by this. So let's see what we have to look at the adjoint operator. Let's see, have I made any mistakes so far? Let's see. So let's see. Let me just check if this is correct. B. So yeah, if I combine these two, okay, let's write. So what is this differential operator? Mt. I just call it Mt. This is the second order differential operator acting on that. Mt is there is a t times 1 minus t d2 by dt2, and then let's collect the t terms, t linear in t and constant terms separately. So the claim is, let's check it if it's true or not. So the claim is this is minus b minus a minus 1 t plus a minus c plus 1. Okay, d by dt. Let's see, is it correct? So look at the t terms. Okay, there's a minus I have taken out. So a plus b plus 1. Now it's wrong here. Something has gone wrong. No. Okay. So they have put a minus sign overall. Okay, overall, because it's written t square minus t. Here I've written. So okay, that's fine. So I put here plus sign. Okay, plus sign. I mean, in that equation 17.23, they have written mt. Their mt is the minus of that. Okay, so that's all. Because it's written t square minus t times t minus 1. So it's a minus sign. Okay. So plus, so that's okay. So you have minus b, but there is a plus 2b, which makes it plus b. And then the remaining minus a minus 1 is that. And a minus c plus 1, correct? So far this is okay. Okay. So what is the adjoint operator? Look at the adjoint operator. Well, this is, so when I apply on the other side, you will get essentially, so sorry, this is, so looking, this is empty. So what do we have? Empty, and the z minus t minus to the minus a, and then we have ft, right? That's what we have, this integral. So I want to move it on the, this empty on the other side. Okay, so it will become z minus t to the minus a, and mt dagger f of t. Of course, in this process there will be boundary terms, but we'll ignore for the moment the boundary terms. And what is the empty dagger is just this quantity is nothing else but d2 by dt2 t1 minus t times f of t. Okay, I mean, look at the first term is this derivative. I mean, this is, you have ft times that, right? Times d2 by dt2. When you take two derivatives, I'll just get that. So this is acting on everything here. And then the other one is minus minus d by dt f of t times all of that. b minus a minus 1 t. Okay. Good. So how do I solve this equation? We want to make this equal to 0, right? That is our aim. Yeah.
So I know you put minus inside. This is in MC column. Here I have minus in factor. No?
I mean, so there, I mean, let's say, let me put here minus empty. Okay. I mean, this is, I've taken out one minus sign overall. So I might as well keep. Anyway, we want to make it 0. So it doesn't matter whether it's minus 0 plus 0, right? So, but so long as there's no relative sign diff problem, no? Relative sign should be the same. Okay, so this is the equation. So let's just call this whole thing as GT. Okay, let's just call this GT. Then we have a very simple equation. No, okay. So first of all, let's see. Okay, even before doing this, so this equation solution is very first of you can already integrate one step because this total derivative terms. There's a so one solution immediately is this. The first step is immediate. So the solution to this equation is d by dt of t 1 minus t f of t equal to the remaining quantity. Because there is one d by dt outside for both the terms, so that I can immediately integrate, right? So that's f of t times all that b minus a minus 1 t plus a minus c plus 1. So that's the first step. But now I need to integrate this. So call this whole thing as GT. So what the equation we have is dg by dt is equal to, well, GT divided by t times 1 minus t. And then I have this factor, which is b minus a minus 1 t plus a minus c plus 1. So now this can be immediately integrated. I mean, you just bring the this 1 over g, so you just get logarithm, and you just this integration is very trivial, right? In fact, again, the idea is to do a partial fraction. I mean, so this you can write it as some a divided by t plus b divided by, say, 1 minus t. So you get this is a times 1 minus t plus bt divided by t 1 minus t. So equating these two, you see that b minus a is equal to b minus a minus 1. Okay, and a equal to a minus c plus 1. So what is, so therefore this implies b equal to this plus that, right? So a cancels, you get b minus c, right? So these are the two. And now I can integrate. So g of t, so log of g of t from here is log of is a log t minus b log 1 minus t, minus because I put here as minus t here, which is equal to, so therefore g of t is equal to p to the power of capital A, which is a minus c plus 1, and 1 minus t to the power of minus capital B, which is c minus b. So that's g of t, and therefore f of t is simply I have to divide by t and 1 minus t. So it just reduces the power by 1. So f of t is t to the power of a minus c, 1 minus t to c minus b minus 1. Okay. So a very simple solution. I mean, if I had not done that trick of removing the z square term, then it will be a really a second order differential operator, m dagger t. By removing this, what has happened is that the first integral I could just do it for free, right? And then it just became a solving first order differential equation. So it became much easier to solve it. Otherwise, you would just, you see, anyway, initially a hypergeometric function itself is a solution of a second order differential equation, right? Now you will take it to some m dagger acting on this f of t, which is unknown again, right? And m dagger is again a second order differential operator. Then you're not gaining much, right? But by doing this, we have reduced it to just a first order differential operator on f of t, which can be immediately integrated. This is the idea. Okay, so we have, and now the only thing which is left over, which I unfortunately, well, I mean, yeah, let's see. I think I will not, it will take me a long time to do this, because surface term, remember. So far what has happened, if I choose this f, then the claim is that, so that then what we have shown is that by doing a partial integration, the answer is 0, provided the boundary terms vanish, right? So what are the boundary terms? We need to know the boundary terms. And I think I will just state I mean, in principle, you can keep track of all that, but you can already see that whatever the boundary term is, there will be always, I mean, after all, what was it? There was mt, and what we had was, originally we had ft, mt, and mt is acting on z minus t to the, what was it, minus a. This was what it was, contour integral. Now I need to do two partial integration, right? Two of this one and one of that. But in each time, you will get basically ft times these things. And for example, let's say the first time you get t 1 minus t ft z minus times d by dt of z minus t to the minus a. That's one term, right? When I do the first partial integration, right? And then there will be a second one, which will give you d by dt minus d by dt acting on t 1 minus t ft times z minus t to the minus a. Okay, that will be coming from there, and from here you will get minus, or no, plus b minus a minus 1 t plus, I mean this combination a minus c plus 1 times ft times z minus t to the minus a. Okay, but I mean all of these ft's. Okay, I mean you can find you can put all this together, substitute this value of ft here, this ft that we have found, and you can see that if you choose the endpoints of this contour, I mean this boundary terms vanish at t equal to 1. I'm not going to, I mean, spend, because it will take me too much time to explicitly write down. So it turns out, combining all of that, it turns out that this expression is basically proportional to t to the power of a minus c. I'm writing down 17.26. Okay, a minus c plus 1 times t minus 1, or 1 minus t times c minus b, and z minus t to the minus a minus 1. Okay, there's some algebra, you need to combine all of that. Okay? substitute this ft there and do all this. So you get that, huh? And then so you want the boundary contribution to vanish. Okay? So depending on the range, the region. So for example, if you choose real C is greater than real B, then clearly at t equal to 1 this vanishes, right? So if you choose, so this vanishes at t equal to 1, and also you can show that this vanishes at, so this vanishes at t equal to 1 and also at t equal to infinity. Okay. To go to t equal to infinity, you see you can just look at the leading behavior. At t equal to infinity, you can ignore that, okay, and then just multiply all of that together. What you get is, yeah, so the condition is real C greater than real B greater than 0. You see, the A cancels, okay, +1 -1 cancels, C cancels. You just get t to the power of minus b for large t. So if b is greater than 0, real b is greater than 0, that vanishes. So with this, so depending on different regimes of these parameters A, B, C, you can choose different endpoints, okay, where this boundary term vanishes. Okay. So in particular for this choice, I can take the integral from 1 to infinity. So 1 to infinity dt f of t times z minus t to the minus a, where ft is that. And that will be a solution of this equation. Okay. But really, I mean, I don't even need to worry too much about it, about this boundary. I mean, this boundary is where this vanishes, because I can always choose closed contours, right? This was necessary if you choose open contour. Okay. But I could also choose closed contours. For example, so if you look at this integrand, so let me write down explicitly this integrand, z minus t to the minus a, and then what we have is t to the power of a minus c, and 1 minus t to the c minus b minus 1. Actually, let me write it as t minus 1. It doesn't matter. Up to an overall constant, I don't care. Overall constants, I don't care. Okay. Between 1 minus t or t minus 1, there is a minus to the power of that. Okay. That's just an overall constants. I'm not worrying about that. So you get this. But if you look at this function that I'm integrating as a function of t, right? As a function of t, for generic values of a, b, c, for generic values of a, b, c, these will not be integers, right? I mean, these powers, for them to be integer, it has to be some special values of a, b, and c, right? But generically, there will be branch cuts, right? So this, if you write down the t-plane, if you draw the t-plane, so here is my t-plane, and so there is a point 0. At 0, of course, it has a branch cut if a minus c is not an integer, okay? 0 at t equal to 1. So here is t equal to 1. This is 0, and t equal to z. So some z. Let's suppose z is. I mean, okay, z could be somewhere here, whatever z is. So there is a branch cut here, right? Z is something fixed as far as this integral is concerned, right? And at infinity. At infinity also there will be, because you can see if you look at the t goes to infinity limit, you get, so it becomes t to the minus a from there, because I can ignore z. This becomes plus a minus c, and then this becomes plus c minus b minus 1. So a, c cancels, but there is b, right? In general, b will not be an integer. So there will be in general branch cut also there. So as a function of t, there are 4 branch cuts. So for example, I could consider an integral like this, a closed contour, which is like this. For example, I go like that, come here, and no, you have to, then you go to a different sheet. There are some various complicated ways you can do. So for example, you go like that, you go like this, and there are various complicated ways you can do, such that finally you come back to the same sheet. You have to come back to the same sheet. That's the point, right? But you can always do it. Okay. For example, let's see. This is, so you can, so if I go around this, come here, and then, so like this here, then go around like that, come here, go around like that, come. I mean, so you can choose various contours in such a way that you see every time you go around some of these branch points, you will find some face. I mean, you'll go to a different sheet. Okay, but then you can go backwards. You see. So first you go one sheet up. Okay, then you go one sheet down. For example, as far as this singularity is concerned, this branch thing is concerned, you come back, and again go in the opposite direction of the first. So you can come back, you see. I mean, okay, difficult to draw. But you know, you can always choose some contours, but you have to worry about the sheets. You see, if you do something like, if you have just one singular point, let's say, okay, one branch point, and if you take a contour like this, and if you come back, you don't gain anything. You'll get zero answer, right? But here you have two branch points. Okay, and in general they'll have different faces. I mean, you know, for example, when t goes around origin, when t goes around 0, you'll get a face e to the 2 pi I a minus c, right? Goes around counterclockwise. Huh? Whereas when t goes around 1, you'll get a face e to the power of 2 pi I c minus b minus 1. Huh? So by playing with so what you want to do is you want to do say around, you choose, okay, maybe I can explain. So you choose a path in such a way, you go once counterclockwise around the origin, okay, you picked up that face, okay. Then you, for example, you can go one counterclockwise or clockwise. So let's say counterclockwise again around 1, so I get this face. Now you come back and you go clockwise around the first one, okay. So that will cancel this face, and then again you come and go clockwise along this. Okay, so then you come back to the original sheet because, right? But in this process, answer is not 0, right? So just think about this. So let's try to draw like this. So here is my 0 and 1. Okay, so first let's say I go around like this. Okay, and let's say this, I call this integral I1. Okay, this integral. Then I go clockwise around the first one, around the t equal to 1. Okay, so this will pick up a phase e to the power of minus 2, because I'm going clockwise now, minus 2 pi I c minus b minus 1. Okay, and then I come back, integrate here. So what will be this integral? This integral will be the same as I1, but with this phase and the opposite orientation, so minus. So this integral will give you minus I1 times e to the 2 pi I c minus b minus 1. Right? Now you go around and say you go clockwise around this, clockwise again around that, and again go along I1. So the first step you got that, second step you got that. Now you go clockwise, so you'll get this phase times the negative of that phase. Okay, so altogether you get e to the minus 2 pi I c minus b minus 1 minus 2 pi I a minus c times again I1. Okay, but no negative sign because now the orientation is the same way. Okay, now I do a counterclockwise along that. Okay, when I go counterclockwise along that and then again come back here, so I will again get the fourth step. I will get minus I1, minus because of the orientation is that way. This phase times I have to go now counterclockwise, so that will get rid of this phase. Okay, so you're left with simply e to the minus 2 pi I a minus c. That's it. And then again you go counterclockwise, so this phase will also disappear and you come back to the original point. But now when you add up these these four things, this is not vanishing. You see, this doesn't vanish, right? So you get something non-zero answer, despite the fact that so it's a closed contour, but you get non-zero answer. I mean, this will be the case if these are really not integers, so that there's really branch cut. If one of them becomes integer, then you'll have, for example, if this guy is integer, okay, then already you see these two cancelled, right? So generically, when they are not integers, Generically, they are not integers. Okay. In that case, you can always construct these closed paths by going around suitably, counterclockwise, clockwise. You know, it should just cancel each other. You should choose a path. So this is the way you can construct closed paths. So this is the integral representation of the. Okay. So okay, fine. How do we go back to this original discussion? Okay, but at least we know that already. I mean, this is the closed path, I said. But already in this case, real C greater than real B greater than 0, I can even choose an open path, 1 to infinity, because of the boundary terms. The boundary term vanishes at 1 and infinity, so I can do that. Okay, so let's focus on this here, and in fact, try to see what solution you will get. I mean, this solves the differential equation, hypergeometric differential equation, as a function of z. But remember, we have two different solutions for two linearly independent solutions. So which one is that? If I do this integral, okay. And to do this, let's. I mean, so let's do the following. 1 to infinity. It's more convenient to, I mean, this is 1 to infinity, right? So it's more convenient to change the variable in such a way that this integral becomes 0 to 1. Okay? That you can do by just taking t to 1 over t, right? So if I write t is equal to 1 over t prime, then as t goes from 1 to infinity, t prime goes from 0 to 1, right? Or 1 to 0, but up to overall sign is the same thing. So this becomes 0 to 1 dt prime, and here you get, okay, we can, so there is a 1 over t prime square from this. I'm not worrying about the overall constants, okay, minus, but that minus changes the thing also. Then here you get 1 minus t prime z to the power of minus a divided by t prime to the minus a, okay, and then here you get t prime plus a minus c from here, and then you get here 1 minus t prime to the c minus b minus 1, and then here you get plus c minus b minus 1, right? T prime. I'm just writing t is equal to 1 over t prime and then taking out 1 over t prime, so you get it, and so on. So this integral is, I'll try to show to you how this is producing this. So this combine everything. So you get dt prime 0 to 1. Now what is the power here? Minus a cancels, minus c cancels. So you have minus b minus 1 plus 2. So minus b plus 1. Huh? Minus b plus 1. So t prime to the b minus 1, right? T prime to the b minus 1. And then you get here 1 minus t prime to the c minus b minus 1, and then 1 minus t prime z to the minus a. Okay? So here is the integral. So let's try to see what happens. So suppose I'm looking at z near 0. I want to see, I mean, this is a solution of the hypergeometric equation. But we want to study the behavior near the various singular points. So let's say z equal to 0. So near z equal to 0, I can just make an expansion of this, right? This, so 1 minus t prime z to the minus a is simply gamma a plus, as we saw before, gamma 1 plus n, okay, and 1 over gamma a, sum over n. Yeah, that's how t prime to the n, because this whole thing is t prime. You see, z is small, t prime is anyway between 0 and 1, so this quantity is also small, right? I couldn't do that in the original thing because t is, even though, I mean, then you have to think in different, I mean, this is more convenient, you see. Now t prime is between 0 and 1, and z is, I'm taking very small. So this product is also small, so you can make an expansion of this whole thing together. So you get it. So now, so what is the, so I have to integrate that, substitute this, so this becomes 1 over gamma A, 1 over gamma, I mean there's a sum n equal to 0 to infinity, gamma 1 plus n, gamma A plus n, z to the n. And then I have to integrate t prime to the n dt prime times t prime to the b minus 1 plus n, so b plus n minus 1, and 1 minus t prime to the c minus b minus 1, 0 to 1. This, do you remember this integral? This integral was giving you the beta function, right? So we can explicitly put all together. So that integral, so the full thing is, okay, 1 over gamma A plus n, gamma 1 plus n, z to the n is there. And then the result of that integral is gamma of b plus n, gamma of c minus b divided by the sum of these two, right? B plus b cancels, so c plus n. That's what we have. Okay, these are constants, so let me take it out. So you have 1 over gamma, I mean n independent. Constant meaning n independent. Gamma A and gamma C minus B, I take out. And this is what you recognize. This is exactly the series expansion for the hypergeometry, FABC Z. So this, up to this overall constants, in fact, even overall constant, you see, for hypergeometric, it was for hypergeometric FABCZ, it was gamma C over gamma A, gamma B, times this expansion, this part. Right? So up to an overall constant, you see this integral, that integral simply gives you FABCZ. Right? In fact, if you want to even normalize it properly, this integral is, so FABCZ is simply equal to this. I have to divide by gamma C minus B. So gamma C minus B and gamma B, gamma C. This is what it is. If you consider this, so you see that gamma C minus B cancels, and you're just left with gamma C divided by gamma B divided by gamma A, which is exactly that. So we can express FABCZ as some constant which depends on ABC times this integral, 0 to 1. That's I mean, of course, in doing so, you see, I have used, I mean, remember beta function, this was beta function provided these exponents satisfy certain conditions, right? So in particular, one of the conditions was that this quantity, the real part of this quantity was positive, right? That's indeed, but this whole thing was true for real C greater than real B greater than 0, right? So in particular, real C minus real B is greater than 0, right? So I mean, otherwise I couldn't have used this beta function thing. You know, I have to use. And similarly, I mean, real B for n equal to 0, for example, real B should be positive. That's what this condition is. Right? So, okay. So, I mean, let's say ignoring these constants. So basically, what we are saying is that when I integrate this expression from 0 to 1, or before changing the variable t to t prime, 1 to infinity. Even this was after changing the variable t to t prime, right? In the original variable, 1 to infinity. Okay. Then you find an analytic function, analytic solution. Okay. The FABC, the solution which is analytic at z equal to 0. Now you can ask the question: can I choose other contours? I mean, this was one particular contour, 1 to infinity, right? If I choose other contours, can I get all the other hypergeometric functions? Okay, and the answer to that is again true. You can do it. So, for example, suppose I want to get the second solution. So let's again draw it like this. So you have 0. Let's put z somewhere here. 1, and infinity. Okay, it is a t-plane. I'm thinking about the t. This is a t-plane, and I have to integrate. So the original expression was t prime. No, before I did the change of variable, what was it? T. Yeah, it was so t minus z to the power of minus a, t minus t to the power of b minus c, right? B, oh, a minus c, sorry. A minus c and t minus 1 to the power of c minus b minus 1 dt. This was the integral, right? And we took it from 1 to infinity. And we saw that this was equal to, this is equal to this quantity, gamma b, gamma c minus b over gamma c times FABC Z. But I mean, I could have chosen, so this contour was between here and here, right? But we have, I mean, 4 singular points, right? I mean, as a function of t, this is the singularity is at 0, t equal to 0, t equal to 1, t equal to z, and t equal to infinity, right? 4 points. And okay, here I just picked 2 singular points and I did the integral from 1 to infinity, right? Well, I could have chosen other. For example, I could have chosen this contour, 0 to z, or I could have chosen 0 to 1, or I could have chosen z to 1. Out of the 4, it's basically combinatorics, 4c2. I have to just pick 2 points, right, and integrate. 4c2 is exactly 6. And those 6 that I mentioned before are exactly this, 6. Okay? So, for example, if I do 0 to z, let's just do 0 to z. Suppose I do 0 to z. Again, I'm not going to worry about the overall constants and so on. I mean, this, so this is basically t minus z to the minus a, t to the a minus c. And since t is going to be, so I put, say, z between, so I will take z to be between 0 and 1. Okay, for convenience, I will just, I'm putting everything in the z also real axis. But it doesn't matter because if you know the values of z, this function for the real values, by analytically you can define everywhere. No? So it's enough to do it there. And furthermore, I'll put the z between 0 and 1. So there is this, and then you have 1 minus t to the c minus b minus 1. Again, I write it in such a way that you see t is, I mean, this I want to keep it positive. Up to an overall face, it's the same as that. dt. Okay, so what I can do, let us just write t goes to t times z. Right? Just write t is equal to t prime times z. Okay. Then this becomes, you can take out z. So this gives you z to the minus a from there. And from here, the change of the measure, you get plus 1. Okay. And then here, you get z to the a minus c. So plus a minus c. And then the integral which is left over, first of all, 0 to z, that is t. But then t prime is 0 to 1. Right? If t goes from 0 to z, clearly t prime goes from 0 to 1. So this becomes 0 to 1. And then you get 1 minus z, t minus 1 to the power of minus a. Right? I took out t prime to the minus a. Right? From here you get t prime to the a minus c. And then from here you get 1 minus t prime z, 1 minus t prime z to the power of c minus b minus 1 dt prime. Yes? That's what you get. And now you notice the a cancels and you get z to the power of 1 minus c. The 1 minus c was the second root of the inducible equation, right? So you get z to the 1 minus c times, what is this? This was, just compare there, this is again a hypergeometric function, right? But with different arguments. I mean, here it's not going to be a, b, c. Just read off from here. Read off from here what it is. First of all, notice that this a was the coefficient of that, right? So this is going to be c minus b minus 1. So what we conclude is that this integral if I taken this contour integral, I mean, this is just a notation. I mean, I have to just make a closed contour, right, in such a way that the boundary terms vanish. So this gives me z to the power of 1 minus c times up to some constant, times f. Well, a is replaced by minus c, so b plus 1 minus c, b minus c plus 1. Right? And then the coefficient b was this plus 1, this power plus 1, which is a minus c plus 1, right? So a minus c plus 1. And then finally, the c is obtained by looking at this power, right? So c is this power. I mean, you have to do this. I don't know if I call this power gamma, then c is equal to gamma plus b plus 1, right? That's what it is. Right?
The power of t raised to t prime and 1 minus t prime.
Yeah, if you add that, then you get c minus 2, right? C, yeah, good. So c minus 2 is the sum of these two powers, right? So c is equal to sum of these two powers plus 2. So this c will be sum of these two plus 2. So a cancels, you get 2 minus c. Okay. And indeed, if you look back at the equation, this was the second solution. This was what we call u2. Okay. You can convince yourself, I mean, please try to do that by choosing now, for example, let's say, if I choose the integral from 0 to infinity, so do this integral, or which is the same as 0 to minus infinity, I mean, the same, then that will give you the analytic solution near z equal to 1, what we call u1 tilde. Okay? And if you had done this integral, you would find the second solution, u2 tilde. Okay? And so on. So, and similarly, the remaining two choices that you have. I mean, now we have considered 4 choices. For example, what is the remaining choice? Yeah, one choice is z to infinity, and the other is from 0 to 1. Those two will give you the u1 double tilde and u2 double tilde for solutions. Okay? This is again just by, like here we just have to just keep changing variable t into some suitable t prime, okay, such a way that you reduce the integral like this, the t prime variable. Okay? This you can always do. Why? Because, I mean, after all, here what we did, I mean, here there's an integral between two singular points, right? Two singular points. I mean, out of this 4, just pick up any 2, and here integral between the 2. But I want to, when I want to bring it in this form, all I want to do is to bring it into a standard 0 to 1, right? Which basically means that those two singular points, I have to map it to 0 and 1. But by an SL2 transformation, you can always bring it, right? So you can do that, and so you can always bring it in this form, and then you get rid of from there what the hypergeometric function is. Okay. So that's a nice thing about it. So all the different solutions are given by the same integrand, this integrand, but just choice of different contours. Yeah, just move the contour, choose another contour, and you get another solution. So it's all kind of unified into one expression here. So, for example, how would you? I mean, so let's see how I could use this. How could I use this? I mean, there are several ways of doing it, but let me just give you one example. You see, from this expression, I can easily compute the value of f a b c at z equal to 1. I mean, this is this solution, of course, has a power series expansion around z equal to 0 with the radius of convergence. If I expand it, as we explicitly saw, if you just expand in powers of z, you exactly get the same the Cn coefficients that was coefficient for in the expansion for the hypergeometric function, right? Same coefficient. which had the radius of convergence 1, right? But now I'm not going to expand it. This is an integral. I'm not expanding in a power series or anything. I can try to go ahead and see what happens at z equal to 1, right? So at z equal to 1, of course, I'll have to assume some range of these parameters. Otherwise, these integrals won't make sense. I mean, already we said that this is one range which allows me to compute the beta functions that we got. Otherwise, you couldn't use that expression that we had. It was only true for this kind of conditions. So for z equal to 1, what we will get here? This integral up to this constants, gamma c over gamma b, gamma c minus b. You get, so this becomes dt prime. So at z equal to 1, 0 to 1, t prime to the b minus 1, and 1 minus t prime. At z equal to 1, these two add up, right? So you get here c minus a minus b minus 1, okay, dt prime. Okay. Now again, this is beta function, right? So you see that provided these are real part of that is positive and real part of this we already assumed real part of b is positive. Now this tells me that if real part of c minus a minus b is also positive, okay, then this integral is simply gamma of b plus 1, gamma of c minus a minus b divided by gamma of so sum of these two, which is bb cancels, so you get c minus a plus 1 times that, times all that. So that's the expression. So we are saying that this FABC1 is simply this, is equal to gamma c over gamma b. Now notice, I mean, you see this is a bit surprising because I mean we are able to actually get the number. I mean, you wouldn't expect that, right, in general, because after all we said that this is going to be, I can express, I mean, near z equal to 1, is better thing to do is to expand in terms of u1 tilde and u2 tilde, which are the power series in 1 minus z, near z equal to 1, okay. So this will be in general a function of a combination of u1 tilde plus u2 tilde with some coefficients, right? Now this one of them is analytic, that's fine, there's no problem. But other guy goes like 1 minus z to the power of c minus a minus b, right? That was the second root of the indicial equation around z equal to 1, okay. But the point is that why I'm able to compute this is precisely because of this condition. Real c minus a minus b is positive. So this is, real part of this is positive. So at z equal to 1, this vanishes, you see. That's why I have and so this vanishes and only that is left over. But that is just a regular analytic solution. So you get this number. But this is true only for this range. So we find this equation, and using this now we can find the linear combination. I will just show to you what is that. So let me just write down. That's u1. Where was that? We had this. I mean, expressions for u1 tilde and no. I mean, here it was minus z. Yeah, 1 minus z. So we had expressions for u1 tilde. I mean, you remember the u1 tilde and u2 tilde expressed in terms of hypergeometric function. Sorry? Yeah, here it is, yeah, good. So u1 tilde is f a b c, a b a plus b plus 1 minus c, comma 1 minus z, and u2 tilde is 1 minus z to the c minus a minus b, and then you have f c minus b, c minus a, 1 plus c minus a minus b, 1 minus z. And say I want to look at u1. So u1 is a u1, I mean, so let's say FABCZ. I want to write FABCZ. So FABCZ is the u1 solution, right? that it should be possible to write it as some coefficient alpha times u1 tilde, which is f a b a plus b plus 1 minus c 1 minus z, plus some coefficient beta times the second solution, right, which is 1 minus z to the c minus a minus b times all that, times f c minus b, c minus a, 1 plus c minus b, minus a minus b, 1 minus z. Okay. So the question now is, how do I compute this alpha and beta? Okay. I can do it by choosing this value. So I know that f a b c at z equal to 0. So just evaluate this expression for z equal to 0 and z equal to 1. You have two equations. You have two unknowns, right? So you need two equations to determine these two unknowns. Constants, I mean, but they are unknowns which we need to determine. So at z equal to 0, this is 1. Okay. At z equal to 0, this argument is 1, and that argument is also 1, but this vanishes anyway at z equal to 0 for this real part of this positive, so I don't need to worry about that. So from the first equation, actually you get the value of alpha. You just evaluate this at z equal to 0, which is 1, and that at z equal to 0 is the same as this argument being 1, which is given there for arbitrary ABC satisfying this condition. Okay. So instead of ABC, now just use these values. And try to see if you can also satisfy again the same range. I mean, real part of that must be greater than that, etc. No? Okay. But I think that just says that real part of 1 minus c is positive, right? That's what it says. Okay. So you will get a value for this. So that you can use that to calculate alpha. Right? Now go and put z equal to 1. For z equal to 1, this is no, there's also at z equal to 0, you have also this, both the things are there, at z equal to 0, right? So you'll get a combination of alpha times this plus beta times, I mean, this is simply 1, beta times this quantity at argument 1, okay? And second equation, at z equal to 1, this drops out because under the assumption that this part is positive, so you get directly an equation for alpha. At z equal to 1, this is 0, so this quantity is simply 1, right? Because f is always normalized, so that at the argument equal to 0, we make it 1. So you just get alpha equal to this evaluated at z equal to 1, which is that quantity. So you see, alpha you already know. And then from the second equation, which is alpha times something plus first equation, alpha times something plus beta times something equal to 1, you evaluate beta. You see? So you can deduce both alpha and beta. Another way to do is simply just doing the deformation of the contour. For example, let's suppose, as we saw, what is, so if I look at this 0, z, 1, and infinity, okay, here's also minus infinity, then this contour integral gives you something proportional to u1, right? This contour, I mean, there are some gamma function which are there in this proportionality thing, but it's some number times u1. I mean that integral. Okay. On the other hand, this integral, so this integral gives you u1 tilde, and this integral gives you u2 tilde. Okay. This is something you should check. I mean, I leave that as an exercise. To show that. But assuming that this is the case, I mean, assuming that you can show it, then you can do the following. You do this integral, I mean, this is the integral u1, right? So let us consider I mean, again, using the residue theorem. No? Consider this integral. You you take this path, go on top of this thing, come here, go around, come here, and go around, come here, okay? Well, this integral, the answer is going to be 0 because I can just do something here, and it has no other singularity. You see, this integrand has no other singularity in the upper half plane or lower half plane. Okay, so again, you have to assume some range so that the semicircle integral does not give you, I mean, should vanish. So there will be some range, which basically says that as t goes to infinity, the powers that add up should be less than something. Okay, there's some condition. So you see that I get one equation, which is this integral plus this appropriate phase that you get times this integral plus this phase times that integral plus that phase times this integral. Right? So for example, let me call this integral I1, I2, I3, I4. Okay. So first equation tells me that I1 plus this phase, which is what was the integrand? T to the power of, what was the integrand f of t? Yeah, this is the expression. T minus z to the power of minus a, t to the power of a minus c, and t minus 1 to the power of c minus b minus 1, right? dt. This is the integrand. So first I do this integral. Then when I come here, you get I2, but now you have to look at t equal to 0. This is I'm going around t equal to 0 branch point, right? So I will get e to the power of I pi a minus c. I pi, not 2 I pi, because I'm only going pi angle. Minus I pi, because clockwise. Okay. Times I2 plus, now I go around t equal to z, so t equal to z. So I get here minus a I. I mean, I already have this phase from the previous thing. I mean, to arrive here, I have to go around this and then go around that. No? So there is already e to the minus I pi a minus c. But on top of it, I have also to consider this phase, right? Which is another e to the power of minus plus. So plus I pi a, right? Because it's clockwise, times I3. I'm just showing to you how you can evaluate this. So you get here I3. And then to go to I4, I need to go on top of it again, this around 1. So all this phase, which is, okay, a cancels here. So you get e to the I pi c from previous ones. And here you get t equal to 1. So minus I pi c minus b minus 1, I4 equal to 0. Right? But you could have equally well chosen another path. Come here, go down, all the way down, everything down. So the second choice is this. And then again do the integral down. And once again, for a suitable range of parameters, that will be made to vanish. So you get another equation, which is just the opposite phases, I1 plus opposite phase, e to the I pi, because now it's counterclockwise. I pi a minus c, I2, plus e to the a cancels, so e to the minus I pi c, I3, and then here c cancels, so e to the power of, okay, I pi, this is my e to the power of minus I pi b minus 1, I4 equal to 0. So you get two equations for this. Okay. Now suppose I want to evaluate, I want to express, let's say I1. Okay, in terms of, or let's say I4 was my U1. I want to express U1 in terms of linear combination U2 tilde and U1 tilde. I want to express I4 as some linear combination of I1 and I3. Okay, and I want to find out what is alpha and beta. Well, all I need to do is eliminate from this I2, because there's no I don't want I2 here. So just take this equation, multiply by this phase, opposite, multiply by this phase, and this equation multiply by this phase, and subtract. So I2 will disappear, okay? And then you'll get an equation which involves only I1, I3, and I4. You can use that to solve for I4 in terms of I1 and I3, right? So this is the way, another way of getting those constants alpha and beta, no? But in doing so, you have to be a little careful, because these directly don't give you the hypergeometric function. There are these normalizations, right? Similarly, this also doesn't directly give you that hypergeometric function. There are some normalizations. You have to compute that normalization first. Then you will get the relations between different hypergeometric functions.